All right, guys, Mr. Mises here, and we are finally to one of the major parts of calculus. We've got really 3 or 4 major things in calculus that we look at, and the first one we're going to start today with limits. So in this lesson, lesson 1.4 is about limits and continuity. So the first video, I'm going to split this lesson into 2 videos. The first one we'll talk about limits graphically, and we'll look at continuity, and then I'll look at one-sided limits using piecewise functions, and then using something called direct substitution to do some limits algebraically. All right, so let's get to it. First, limits and continuity. Let's take a look at this graph here. All right, so I have this graph, and the basic idea of a limit is that a limit is a y value which the function approaches as the x goes closer and closer to another value as well. So let me put the screen up here so you can see my hand movement. So as we get closer and closer, as the x values gets closer and closer to a value, what does that y value approach? All right, that's what a limit is. Now, it's very important that you understand that you at least be able to write the way that we write limits. And this is the technical way to write a limit. It needs to be written that way. It can't be written, you can't just go x approaches c. You can't just say x arrow c. You can't write the word limit out. You should write it like a mathematician would write it, with lim, and then x with an arrow to a number. This is the limit as x approaches c of f of x. Okay, so the limit of f of x is equal to some number L, all right, some y value. So let's take a look at this graph and take a look at what I mean by a limit. So the limit as x approaches -4. So if you look here, here's our function f. It's all over the place. Here's x equals 4. We're not looking at x equals 4. We're looking at x equals -4 right here. Now, if I was walking along this graph, as x gets closer to -4, my y value is getting closer to 1. Right? So my limit is going to be 1. That's what my y value gets closer to. So as my x gets closer to 4 on the graph gets closer to a y value of 1. F of 4, that's the point, that's the actual y value of x equals -4 on the function. Okay, so this is, since it's a solid point, this is also going to be 1. The limit as x approaches -1. So here's -1. As I approach -1, as x gets closer to -1, what does the function y value get closer to? It gets closer and closer to 4. So the limit is 4, even though the function value itself is going to be 1. And I get that because right here, here's -1, right? F of -1 is this solid dot right here at 1. So my function value, f of -1, is actually 1, even though my graph gets closer and closer and closer to a y value of 4 as x approaches -1. That's the difference between a limit and a function value. Let's look at limit as x approaches 2. So as x approaches 2, the y value is going to approach 1. And f of 2, notice here that there is no point that defines f of 2. There's no defined f of 2. There's no point solid. We've got an open circle there, so I'm going to write D and E. It does not exist. Okay, I got all this blue stuff here. I'm going to erase this so we can see the next one a little better. The limit as x approaches 3. So notice here we've got a vertical asymptote at 3. And as I approach 3, I'm going to go down forever. As I approach through here, I'm going to go down forever. In fact, these y values are going to get negatively larger, I guess you can say, negatively larger, and not approach 3. They're not ever going to touch 3. So I would say that this limit is, you can either say this limit is negative infinity, or you can say that this limit does not exist. All right, the limit does not exist. There is no limit. It's going on forever, right? If I have no limit in life, I can go on forever. Same thing here. The limit does not exist. F of 3 also does not exist because there's no function value defined for 3, for x equals 3. All right, what about x equals 5, or as x approaches 5? Here's 5. As x approaches 5, well, as I approach 5, as x gets closer to 5 this way, the y value looks like it's getting closer to negative 1. But as I approach 5 this way, the y value gets closer to 2. So I've got a problem here in that it doesn't really approach a single y value. So if it doesn't approach a single y value from either direction, it goes to two different ones, we're going to say that this limit does not exist. All right, it has to go to the same y value. Okay, it's got to approach the same number. F of 5, that's going to be 2, because this is where the solid dot is. Now, the example that the problem that I just did here with the 5, I'm coming from two different directions, right? Here I'm approaching from the left side of the value of x equals 5. This is the left and this is the right, and I'm approaching from the right here, and here I'm approaching. Let me zoom in here for you. Here I'm approaching from the right, from the right of x equals 5. And this is from the left of x equals 5. Well, those are actually called one-sided limits. So I can do a one-sided limit just from the right, and I could say that that's 2. Or I could say it's just from the left. The limit as x approaches 5 just from the left is going to be equal to negative 1. Well, we do have notation for that. The notation for that is if I have a little minus sign right above the number, okay, that means from the left. So we decided that was going to be negative 1. And if it's a little plus sign there, it's from the right. Okay, and we decided that was 2 in our example. Okay, so where does this kind of lead us? Well, this leads us to an important concept called continuity. And continuity, just informally, a graph is continuous if we can draw the graph, without lifting our pencil. So if we just kind of have like a smooth curve and we can draw the whole thing without lifting our pencil, then we're going to have something that's continuous. All right? It basically means that the whole graph is connected. Now, if we have things that are disconnected, if we have a graph that's disconnected, maybe it has holes or it has vertical asymptotes where it goes up like this, and you have to take your pencil off. Or you have jumps in it, like you have a line like that, and then you have to jump to the next one, and a line like that. Got to take your pencil off. Those are called discontinuities. Those are breaks in the graph that cause the graph to be discontinuous. So we'll talk about those as well. For now, we're really interested in graphs that are continuous. So let's take a look at my last example here. List the x values of the discontinuities of the function f of x that we graphed above. So if we look at the graph, we're looking for any time that we have a break. So as we travel along this graph, right, our first break is going to be right here. We gotta take our pencil off to make a circle and then take our pencil back on. So we've got a break here. As we travel along again, we've got another break here. As we travel along again, we're going to have to pick our pencil up, and we have another break here. And then as we travel along again, we have another break right here. So we've got breaks at these x values. All right, so we have breaks at x equals negative 1, 2, 3, and 5. Those are all the places where we have what we call discontinuities. So just a quick summary of some vocabulary for discontinuities. All discontinuities can be classified as either removable or non-removable. Removable discontinuities occur when the function has a limit, but there's a hole in the graph. So if we had a hole in the graph, we could basically shade the hole in, then we can remove the discontinuity. A non-removable discontinuity is when the function, the limit, really, it doesn't exist. So when we have a vertical asymptote or we have a jump in the graph, we cannot remove that discontinuity. So those are called non-removable discontinuities. Okay, guys, so in this video, you should have learned what a limit is, that it is a y value, how to find limits using a graph, so graphically, the difference between a limit and its function values, what a one-sided limit is, and the basic idea of a continuity and where we could see discontinuities on a graph. In the next video, we'll talk about direct algebraic substitution and using those one-sided limits in piecewise functions. Okay, till next time, see you guys.